Good morning. Today, let us see the drain current equation, the derivation for the drain current equation. It shows the relation between drain current and VDS voltage and also with some other parameters. So to derive the drain current equation, it is better to consider first of all the construction of the MOS transistor. Here the slide representing the construction of the MOS transistor. This region is called substrate region, whereas this is the source and this part is called drain region. And in between source and drain, the region is called the channel region. Upon the channel, the layer is called silicon dioxide layer. This is the silicon dioxide layer. Over the silicon dioxide, a polysilicon layer is there, right? And this diagram represents some parameters like L, W and capital D. Here L is the length of the channel, W is width of the channel, and capital D is the thickness of the oxide layer. Okay. Now see the notations for different parameters which linked with this equation, that is drain current. L, already L is the length of the channel and W is width of the channel, a transistor. D is the thickness of the oxide layer. Epsilon is the permittivity of the oxide layer. IDS means drain to source current. VDS, drain to source voltage. Q is the charge induced in the channel, and tau is the electron transit time. Okay, these are the different parameters linked in the drain current equation. Okay. Now let us see how the current will flow in the MOS transistor. We all know that based on the operation, when the channel is existed between source and drain, by the application of drain to source voltage, the current flow will occur. Okay. Therefore, the drain current is expressed as, based on the fundamental formula, that is by taking the relation between current, charge and time. Current equal to the charge induced in the channel divided by electron transit time. The charge induced in the channel divided by electron transit time, that is I equal to Q by T. So with reference to this equation and MOS transistor, IDS equal to QC divided by tau, and it is treated as equation 1. Okay. So where the tau is the electron transit time and it is expressed again using the relation between time, distance and velocity. Okay, that is T equal to S by V. Okay, with reference to this transistor, it is expressed as tau ds equal to length of the channel divided by velocity. Length of the channel divided by velocity. Therefore, L by V. And here V is the velocity and is expressed as mu EDS. Mu EDS. Where mu is the mobility and EDS is electric field strength between drain and source. Okay, mu is the mobility, mobility of the charged particle. It may be hole mobility or electron mobility, that depends on the type of MOS transistor we have considered. And EDS is the electric field intensity due to applied VDS voltage. Okay, therefore EDS we can express as VDS divided by L. Okay. By the back substitution, the velocity equation you can express it as mu VDS divided by L. And therefore the time tau equal to L square by mu VDS. L square by mu VDS. This is considered as equation 2. And now substitute equation 2 in equation 1. Therefore the current IDS equal to mu VDS QC divided by L square. Mu VDS QC divided by L square, right? Now considering the charge with reference to different regions of the MOS transistor operation. Okay, from the characteristic curve, the main regions are saturation region and saturation region. These two are separated by a pinch off point. Before the pinch off point, the region is referred as the non-saturation, and after pinch off point it is considered as the saturation region. Okay. Now first let me take the non-saturation region, okay, and see how much charge is induced, and let us see the expression for the induced charge. Okay, that is QC equal to Eg epsilon area. Okay, Eg epsilon area. Area means here length into width of a channel. Length into width is referred as area. Okay, so Eg epsilon WL. Okay, where what is Eg? This is the Eg means Eg is the electric field intensity because of the gate potential. This electric field intensity between gate and channel, actually Eg is the electric field intensity between gate and channel due to the applied VGS voltage. Okay, therefore uh, relation between the electric field intensity and the applied voltage is actually E equal to V by L. V by L. Okay, here the electric field intensity is between gate to channel, means that is because of the applied voltage at the gate or effective voltage at the gate to the channel drop, okay, and here the channel drop is not because of the channel drop, the VDS voltage is considered as the average voltage. Okay, because of channel drop, the VDS drop is VDS divided by 2. This is the average VDS voltage, and the effective voltage is VGS minus VT. Okay, therefore the EG equal to VGS minus VT, that is the effective gate voltage, minus the average VDS is VDS divided by 2 whole divided by D, represents the electric field intensity between gate and channel. Okay, therefore the Q is expressed as, so epsilon of insulator epsilon naught WL by D into VGS minus VT minus VDS divided by 2. Okay, so this is the equation and considered as equation 5. Now substitute this equation 5 in equation 3. The current I becomes mu VDS by L square into that Q equation. Okay, after rearranging, this IDS equation is appeared like this. Okay, appeared like this. Here what we have made, we separated all the constant terms, like mu epsilon of insulator, epsilon naught divided by D is this is the constant. Okay, and it is considered as K here. Therefore IDS equal to K W by L into VGS minus VT minus VDS divided by 2 into VDS. Okay, and IDS also expressed as beta into VGS minus VT minus VDS divided by 2 into VDS, where beta is KW by L. Okay, KW by L. So this is the way are different forms of representation of IDS equation. Okay, but this is the equation in which region? Non-saturation region. Similarly, coming to saturation region. Okay, in the saturation region, what happens is, okay, before going to in the saturation region, here also the IDS represented in terms of gate to channel capacitance, okay, which is given as like this. The gate to channel capacitance EG equal to, because the gate to channel capacitance is equal to the parallel plate capacitance. You know the formula for the parallel plate capacitance is epsilon A by D. Okay, apply that relation here. What happens is, here area means W into L. So WL into epsilon divided by D. Okay, that equal to you can express as KWL by mu. Therefore, in terms of CG, the IDS equation you can write like this: CG mu by L square into that voltage term. Okay, and also the IDS is expressed like in terms of gate capacitance per unit area. Gate capacitance per unit area is represented as C naught. Okay, therefore IDS equal to C naught W mu by L into voltage term. Okay, like that the drain current expressed in terms of K, in terms of beta, in terms of Cg, and in terms of C naught. Okay, anyone you can remember, no need to write the equation in all this. Based on the question asked, you have to express up to that only. Okay, now coming to saturation region. In saturation, the saturation, it starts when VDS equal to VGS minus VT. Okay, therefore the saturation starts at VDS equal to VGS minus VT. Therefore the IDS equation expressed as, after simplification, we are getting it as Kw by L into VGS minus VT whole square divided by 2. Okay, in the above relations, if you substitute, instead of VDS, if you substitute VGS minus VT, it becomes like that, VGS minus VT whole square divided by 2. So in terms of beta, how can you write? IDS equal to beta by 2 into VGS minus VT whole square. Similarly, here also you can express in terms of Cg and C naught. Okay, that is the drain current derivation. Okay.